In this lecture I want to talk about one technique of solving partial differential equations, and it is a very general method that you have been using in various I am sure you have been using in quantum mechanics, but this is a very general technique to solve partial differential equations. So let's use this, and I'll take the example of the wave equation. Okay, so let me take the wave equation. So the wave equation we wrote as the Laplacian of u. Okay, this is equal to 1 over v square dou square u by dou t square. Okay, so this is a 3-dimensional wave equation. The 1D wave equation, okay, so this will be used. Suppose you have waves in a medium, okay, then this describes the propagation of waves in a medium. It could be sound waves through a medium or so on. The 1D wave equation is where your spatial dimension is only 1. So what you have is you have dou square u by dou x square, and u is only a function of x and t in this case. So here u is a function of r and t. In a 1D wave equation u is only a function of x and t. It is still a partial differential equation. Okay. So it is still a partial differential equation, and you can write it in this form, 1D wave equation. Let us consider the 1D wave equation, and let us try to solve it by method of separation of variables. So according to the method of separation of variables, we look for a solution u of x t that is equal to some function that is only a function of x times some function that is only a function of t. Okay, so this is a function only of x, this is a function only of t. Okay, so x of x is a function only of x, t of t is a function only of t. Okay, so what we did is we separated it into, we wrote this total function u of x t as a product of two functions. Okay, one which is a function only of x and the other which is a function only of t. Okay, now the first thing you might think is that can you always do this, and suppose u of x t is equal to 3x square cos t. Okay, then we identify, we can choose, then what we will say is that you will say x of x is equal to 3x square, okay, and t of t is equal to cosine of t. Okay, you could also say x of x is equal to x square, t of t is equal to 3 cos t. So I mean you can do various other combinations. You can say, for example, you could also say x of x is equal to x square divided by some number a, and t of t is equal to 3 times that number cos t. So the message is that these constant factors are not, constant factors can be, you can always absorb it into one of the terms. Okay, so the message is that constants, factors can be manipulated. Okay, so you can put it wherever you want, and for most part we will see that we do not really bother with the constants. Okay, but now you take another example. So let me show that another example. Suppose u of x t had the form, let us say 3x square cos x t. Okay, so if you had something like this, then you cannot separate into x of x times t of t. Okay. So what I want to say is that separation of variables need not always hold. Okay. So there might be solutions that do not have. Okay. So the strategy is so how do you know whether an equation you can separate the variables or you cannot. Okay. So what we do is our strategy is to look for separable solutions. Okay. So there might be other solutions which are not separable, we will look only for separable solutions. Okay. So with this strategy, now let us go to the wave equation. So if you have u of xt is equal to x of x t of t, then first thing you will say is that dou square u by dou x square is equal to t dou now I will have a second derivative with respect to x, okay, that is d square x by dx square. X is notice that x depends only on x, so it is an ordinary derivative, okay, and t depends only on t, so we will just take it out. And similarly dou square u by dou t square is equal to x d square t by dt square. Okay. And when you substitute these in the wave equation, okay, what you get is t times d square x by dx square is equal to 1 over v square into x d square t by dt square. So our wave equation, once you make that substitution, it has this form. So what can you do? You had a differential equation that I will just write the original differential equation. Your original differential equation was dou square u by or dou x square is equal to dou square u by dou t square into 1 by v square. Okay, so this was the original differential equation, and now we have this differential equation. So where do we go from here? What next? Okay. Now what we do is after this you divide both sides by x times t. So when you do that, then what you will get is when I divide this by tx, the t will cancel, so I will be left with 1 by x d square x by dx square is equal to 1 by v square times 1 by t d square t by dt square. V is a constant, that is the speed of the wave. Okay. So now this is the most important part of this method, of the method of separation of variables. So what you do is notice that the right hand side, I will just copy it again in this, or we will just write it here. So the right hand side is a function only of time, okay, because t is a function of time, d square by dt square of a function of time is also a function of time, and t is also a function of time, v is a constant. Left hand side is a function only of x. Okay. So if you have left hand side being a function only of x and right hand side being a function only of t, and they are equal to each other, okay, since they are equal, that necessarily this can only happen, this can only be a function of x, this can only be a function of time. So the only way they can be equal is if both LHS and RHS are independent of x and t, okay, or in other words both LHS and RHS are a constant. So what we are going to do is we are going to demand that the left hand side is a constant. So if the left hand side is a constant, you get 1 over x d square x by dx square equal to, I will just call it c, and the right hand side you will get 1 over v square t d square t by dt square is equal to c. So thus both the left hand side and the right hand side are constant, and now what happened is you get two ordinary differential equations. After separating variables, this is an ordinary differential equation that only involves x, this is an ordinary differential equation that only involves t. Okay. So you have these two ordinary differential equations, okay, and basically you have converted your problem of solving the PDE to a problem of solving two ODEs. Okay. Now this is a general strategy. This strategy of separation of variables is something that you will use for various differential equations, okay, and in fact this is the, in all the problems, okay, we will always assume, so at least in this course, okay, we will always assume separability. Okay. So for example, if you take the Schrodinger equation for a particle in a 2D box, okay. So this is given by minus 2D box between then I'll just write the equation, okay, then we will discuss it, okay. So you have dou square psi by dou x square plus dou square psi by dou y square equal to E psi inside box. So when you have this, okay, then what is done is you write you take this and you write psi of x y, psi is a function of x y in that, I write it as x of x times y of y. Okay, when you do this, then what you will get is this equation will nicely factor out, okay. So if you what you will get, when I take the second derivative, okay, then I just have d square by dx square. So let me write this in a slightly different way. So I will write d square by dx square of x y of y plus dou square by dou y square of x y of y is equal to minus 2 m e by h cross square, and what I will get is psi is x of x y of y, okay. And what you notice is that since this is separable, I can write this as y times d square psi by d square x by dx square. So y times d square x by dx square, okay, plus x times d square y by dy square is equal to minus 2 m e by h cross square x times y. And now if you divide by x y, then what you will get is that d square x by dx square into 1 by x plus d square y by dy square into 1 by y is equal to minus 2 m e by h cross square. Now what you notice is that in this case this is a function only of x, this is a function only of y, okay, and this is a constant. So that implies that 1 over x d square x by dx square is equal to C1 and 1 over y d square y by dy square equal to C2, and C1 plus C2 is equal to minus 2 m E by h cross square. And what is done typically at this point is that you use a notation, choose C1 is equal to 2 m E x divided by h cross square. Okay, so this is define Ex. C2 is equal to 2 m E y by h cross square. So you write it with a minus sign. So you write it in this form, and the reason for doing this is that what you will get is you will get two equations. You will get two equations. So the first equation will be d square x of x divided by dx square. Oh, let me, d square is equal to minus 2 m E x by h cross square psi, or not psi, x of x, and you have a very similar equation, d square y of y divided by dy square is equal to minus 2 m E y by h cross square y of y, and you have E x plus E y equal to E. So, E x and E y have a physical interpretation as the energy in the x direction and the energy in the y direction, or the energy in the x part of the motion and energy due to the y part of the motion. So what we did was we converted our PDE into two ODEs, okay, and each of these can be solved individually. This is a second order ODE. Okay. Similarly, this is also a second order ODE. So this is the general strategy, okay, that we are going to use. Okay. Now in these cases the separation was very easy, okay, because your Laplacian just had a second derivative with respect to x and second derivative with respect to y. Okay. Now you can imagine that separation can be more complicated. Okay. So for example, let us consider the hydrogen atom problem in QM. Okay. So here we use spherical polar coordinates. Okay. So now the Schrodinger equation looks like minus h cross square by 2 m E. Okay. E is the mass of the m E is the mass of the electron, and now what you have is Laplacian, and the Laplacian in spherical polar coordinates has this form 1 over r square dou by dou r of r, or r square dou by dou r of, now psi is a function of r theta phi plus 1 by r square sin theta dou by dou theta of sin theta dou by dou theta of sin theta psi of r theta phi plus 1 over r square sin square theta, and what you have is dou square by dou phi square of psi of r theta phi. This is equal to E times psi of r theta phi. Okay. Now in this case, when you separate variables, you write psi of r theta phi is equal to a part that depends only on r and a part that depends on theta and phi. The part that depends on theta and phi I will write as s of theta t of phi. Okay. And I will actually separation of variables in this case is slightly more tricky. Okay. So when you go ahead and you substitute, okay, so what you will get is Okay, again I will take the h cross square and 2 m e on the right hand side. So what I will write is 1 over r square dou by dou r of r square dou by dou r of r s t plus 1 by r square sin theta dou by dou theta sin theta dou by dou theta of r s t. Okay. Now let me simplify this. So the s and t part in this case, okay, I can take it here outside s t. Okay. Now this derivative depends only on theta, so I can write this as sin theta s, and I can take t and r here, plus now I have 1 over r square sin theta, and what I have is r s dou square by dou phi square of t, okay, and all these partial derivatives will become ordinary derivatives. Okay. This is equal to E times r s t. Now if I divide by r s t, if I divide by r times s times t, okay, then in the first term the s t will cancel. Okay. So what I will have is 1 over r square dou by dou, now let me write it explicitly as d by dr of r square d by dr of r plus 1 over s r square sin theta, and let me write d by d theta of sin theta d by d theta of sin theta times s plus 1 over r square sin theta times a t d square t by d phi square is equal to E. Okay. Now what you notice is that I will just do one part of this separation, is that here this is only term which has phi dependence. Okay. So this is the only term that has phi dependence, and so immediately you can say that this phi dependence has to be a constant. Okay. So you have sum of 3 terms, and you have on the right hand side you have something that is independent of phi. So obviously this phi dependent term has to be a constant. So this implies that 1 over t d square t by d phi square equal to constant. Okay. So this is one of the things that we will do, and so this implies that t of phi is equal to we will just write it as e to the I m phi. Okay. So this constant you can show that it should be equal to minus m square, and eventually after some work. So after some work you will get t of phi should be e to the I m phi. Okay. And with some, I will not write the, as I said earlier, that you can always put a constant factor in front of this, but we will not bother with that. Okay. And for various other reasons, okay, m has to be integer. Okay. So in this way you can separate and you can solve for t, and then once you solve for t, then you eliminate t from this equation. You still have r and s, okay, but you notice that this term depends only on r, okay, and so the theta dependent terms are only there in the second and third. Okay. So what you can do is you can set this part, the theta part, to a constant, okay, and then you can go ahead and solve that equation. Okay. So what is done is that so the second and third terms have the theta dependent terms. Now what you will get is what is done after this is that you write 1 over t d square t by d phi square is equal to minus m square. Okay, you can work this out. Okay, so if you take t of phi equal to e to the im phi, then d square t by d phi square is just minus m square t. Okay, and then if you divide by t, you will just get minus m square. Okay, so then what your equation becomes is that you can replace this whole thing by just minus m square. Okay, and since this term depends only on r, then the remaining term has to be the theta dependent term here has to be a constant. So then what I can write is that I can write 1 over s sine theta square sine square theta, there should be a square, there should be a square in front of the t term. Okay, so there should be a sine square theta there. Okay, so what happens here is that you have 1 over s sine theta. Okay, I am not bothering with the r part. Okay, times d by d theta of sine theta d by d theta of sine theta s plus, or no, now it will become minus m square divided by sine square theta equal to constant. Okay, and now this is an ODE in s of theta. Okay, so this is a ODE in s of theta. Okay, and you can solve this. Okay, so you can solve this, and this gives you in terms of associated Legendre polynomials. Okay, and then once you have the ODE in S, okay, then you use that solution. Okay, and then you what you are left with after you put the ODE for S, what you will get is you will get a differential equation in R. Okay, now incidentally I can just tell what this solution looks like. So this solution after lot of work is that is constant equal to L plus 1 h cross square. So L is just L plus 1, sorry, is just L plus 1, where L is an integer. So finally so this is something that you will see in your quantum mechanics course, but what you will eventually find after all this is that L has to be an integer and this should be a constant. Okay, and so now the final differential equation in R has a form 1 over r square d by dr of r square d by dr of r plus L plus 1 is equal to minus 2 m e by h cross square. Okay, so let us just go back, see where we started. So we had this equation, we took the minus 2 m, so we are left with this part, and then there should be an r square, L plus 1 divided by r square. Okay, I should mention one other term. Okay, there is one other term that I had missed out in the Schrodinger equation. Okay, so there is the potential energy term. Okay, so the potential energy term is a function only of r. So it is 1 over 4 pi epsilon E square by r. Okay, this is a function only of r. Okay, so this won't contribute to the remaining terms. Okay, so let me just call this V of r. Okay, and so I just had to carry that V of r here. Okay, it won't affect this equation, it won't affect this equation, but you should have another term. So E minus V of r. Okay, so that's what the equation will look like. Okay, so the potential energy term only on r, only on the radial coordinate, it should be a minus sign. Okay, so this is the attraction between the electron and the nucleus. All right. So finally what happens is that this is the radial part of the Schrodinger equation. This is a ODE in R of R. Okay. So this is how the separation of variables takes place, and you can see that when you are dealing with Cartesian coordinates, usually things look simple, okay, but there are certain problems that are not, where Cartesian coordinates are just not convenient, and this hydrogen atom was one problem, because you had a center, the nucleus was at the center, and your electron was radially located outward from the nucleus. Okay, it was radially, so it made sense to use spherical polar coordinates which were centered at the nucleus. So you could have other problems. Okay, the most common example is like you could have something like a circular drum. Okay, so if you are looking at the wave equation of a drum, in that case you will be using cylindrical coordinates, or you will be using plane polar coordinates. Okay, and in that case too the separation of variables will become a little more involved. But what I want to emphasize is that once you have done the separation of variables, okay, then you get back ordinary differential equations, and these ordinary differential equations can be solved using the methods that we have already seen. Okay, but it's not always straightforward to get this separation of variables. Okay, so in the next class we will look at the nature of solutions. I'll take the particular example of a circular drum. Okay, because this is a very, it illustrates, I mean we will see the whole machinery of not only of separation of variables, but we will also see of actually solving the PDE. Thank you.